Hey everyone, this is Kai Werner from Confluent. Today I want to talk about IoT architectures for digital twin with Kafka and event streaming. So I will talk about how to combine this with other technologies and products to build an open, scalable and reliable platform for digital twins. The key takeaways of the session are that a digital twin merges the physical and the digital world. That's mainly why we're doing it in many different industries, including manufacturing, but also other scenarios like healthcare. And Apache Kafka is a key component of that very often in the meantime, because it provides an open, scalable and reliable infrastructure for building a digital twin. And finally, last but not least, it's also important to understand that event streaming complements other IoT platforms and technologies. So it also connects to other backend applications and databases, of course. So building a digital twin infrastructure with Kafka doesn't mean that you don't need anything else. And this is exactly what I will explain today in more detail. Therefore, let's take a look at the agenda. First, I will cover the details about what a digital twin is, what are the use cases, and then I will talk about the challenges to implement this. Therefore, then I will discuss different IoT platforms and how Kafka fits in here as event streaming solution. Then I will discuss different architectures because you have so many components as an option in IoT. Let's talk about different architectures and also for edge, for hybrid, for global, and how to combine Kafka with other technologies. And finally, I will talk about one example about building a digital twin for a connected car infrastructure so that you see one specific example. Let's begin with the discussion about what a digital twin is and when you might want to use it. First of all, I have here one slide from McKinsey, which is showing very well how the business is changing, also for companies like car manufacturers or industrial automation and all these companies which produce things or provide any physical service. So this is completely changing these days, and to differentiate, especially compared to many countries which provide very low-cost things, you have to differentiate by providing digital services. This will get much more significant so that you can be successful in the future. Here you see in the end on the right side how services and software are getting more and more important compared to the machinery and the physical things. And this is really true in more or less every industry where you sold physical things in the past without services. And this is also then the core motivation for the digital twins. So what is a digital twin? Actually, it's merging the physical and the digital world. That's what I can define it on a high level. But honestly, it's actually not even always a physical thing. So sometimes we even want to get a digital copy of a process or of a service for your customer. So it's not necessarily a digital or physical thing, but often, of course, it is. Like you see on the left side, some examples for a car or an airplane or a robot. But it can even be something like a human, for example. And therefore then you have plenty of use cases where a digital twin is helpful. So you can use it for examples like predictive maintenance and downtime reduction, but also for many other things like what-if simulations for the future. And this is not just important for machinery, but for many other scenarios like urban planning or Medicare. And then you can also improve your services with building a digital twin and making a better customer experience. So a great definition is that a digital twin is a living model that drives a business outcome. And with these kind of different definitions of a digital twin, we also need to understand that there is a specific granularity you have to think about. This is greatly represented by MathWorks in a YouTube video, where we can see that a digital twin can be either one specific component, or it can be a system of different components, or it can even be a system of systems. So that's what you can see on the left side. And then also, even for one specific component, you might even build different digital twins, as you can see on the right side. For example, one for doing fault classification and one for estimating the remaining useful life. So there is many different kind of digital twins you can build. And also you need to keep in mind that a digital twin is just a replication of a physical asset. However, actually what we are typically thinking about is the whole entire life cycle of the thing you want to get a replica from. So it's really thinking about continuously evolving and improving the products and the services. And this is actually what the literature means with digital thread. However, a digital thread, which you can see here in this picture, it's a great picture from Eurostep. However, the point is that in the literature, often people simply talk about a digital twin, even when they mean a digital thread, so the whole entire life cycle. And therefore, in this talk, I always say digital twin, but in many cases, also actually what I really mean is the whole life cycle, including all the processes to leverage the digital copy. And therefore, you can always also say digital thread. In this presentation, we only use digital twin as a term. Here now we have a few examples of digital twins, and intentionally I used different industries and different use cases. Digital Singapore is a great example for a digital twin of a smart city. This can be used for many different things like urban planning, for example crowd simulation, or for example for collaboration between different people in the city and decision makers for making the right decisions and planning. Also for communication and visualization, for example with the people and the planners living in the city. And therefore you can also combine it with partners, like for example for an analysis of the potential for solar energy production. So it's not just the city and government itself, but they are also working with others on this. Another example is a smart infrastructure. So this is one example from Siemens, but many other vendors have similar things. So Siemens actually calls this building twins. So they are specifically focusing on buildings in this kind of part of their division. And this is also pretty interesting. It's used to build safer, more secure, and more efficient and resilient buildings. They are more and more connected, so the buildings themselves, the things in the buildings, and therefore you can do continuously interaction and learning and adoption to create environments that care about everything happening there. And this is really therefore also following the entire digital building life cycle to improve the buildings, to make the next building better. So as you see here, it's from design to construction to operation and finally even to demolition. Another example is a connected car infrastructure. Here is one example from Audi. And this is also used for so many different use cases. So you ingest all the data from the cars into some data center or cloud infrastructure. For example, for doing real-time data analysis, to communicating with the customer, to do things like cross-selling or customer care. But it's also used, for example, for swarm intelligence, because you get the data from all the different cars. And then again, you might work together with the smart city to even get data from different cars from different manufacturers. So you also want to collaborate with partners like a city or maybe like a food service. And another use case here obviously is also predictive AI, for example for predictive maintenance, to provide the digital service to recommend to a person to go to the service and repair shop because the engine might break or because you need your service. And the last example is about healthcare. So here we are twinning the human body to enhance medical care. And this is another great example, because without being in close proximity to the person, which can even be at home, for example, you can test the impact of changes of the performance of doing something. Like you can give another kind of medicament to the person, or you can make a decision what to do next with the person. And therefore you can use smart machines and get the help of these algorithms to do simulations and real-time monitoring of the patients. And this is also a huge scenario in healthcare where a digital twin from every single person can help. And then, as you can imagine, also combined, for example, with a smart building, so the hospital, this combination of all of this provides so many powerful use cases. And having talked about all these use cases, there is different studies. Here's one from IoT analytics research, where you can see that in 2020, the biggest market is still Industry 4.0, which means things like manufacturing, for example. So the connected industry is the most important one today, but we see more and more projects also, for example, smart cities or healthcare or mobility, but even also other industries like retail and insurance. So it's really getting interesting to get digital twins for almost everything and can add huge added value. Therefore, when we talk about digital twins, it's always important to also understand the relation to AI or machine learning. So these are really complementary concepts. And if you think about that, if you have a digital twin of an asset, you continuously want to feed the new information in from that asset in real time and process it and leverage it to make simulations or recommendations or predictions. And this then is really implying that you also use some kind of machine learning. Of course, for simple use cases, you can also use some simple business rules, but typically it's some more advanced algorithms like deep learning or like any other statistical methods which you want to apply in real time at scale to your assets, whatever the use case is. So machine learning and digital twins are often related to each other. Here is one great example, again from Networks, which they presented in their YouTube video, where they applied a digital twin and AI together. Here is a few examples. So you can either do physical-based modeling, where you really take a look at the hardware and use the generated data to do something, or you use data-driven modeling for doing analysis and predictions. Let's take a look at a few examples here. So for data-driven modeling, you can, for example, use existing data to calculate the remaining usability of the life of the machine which you have. There is then different algorithms under the hood. I don't want to go into too much detail here, but you can use the existing data to optimize the maintenance of and the schedule and the planning of your machines. On the other side, for physical models, you can use this, for example, for what-if scenarios. So you take some hardware and use the sensor information and use that to correlate and predict some new things to make simulations based on the real data from the hardware. And then there is algorithms which you leverage both physics and data-driven information, like a Kalman filter. So there is many different examples, and this is just 3 of them to give you a feeling about how you can apply machine learning and statistical models to leverage it in a digital twin to get benefits out of that. And with this, let's now talk about the real world challenges, because digital twin, that sounds great, but it's not that easy to implement this in the real world. First of all, if you take a look specifically at automation industry, well, automation industry is a very different thing that many of this audience of this video here know from software development. So things are typically built for 20, 30 or 40 years. They are not agile. You cannot simply change things. And also, they are not just legacy and very old. They are often using very complex and proprietary protocols. So it's really hard to integrate with them. And also with that, it's typically monoliths or something which is not really scalable and often not real time. And often it doesn't have any kind of security features. And therefore often it's also not connected to the rest of the factory or world because it's not secure to connect it. And so it's separated from everything else. And this is here not a big example of automation industry, which is the key use case for digital twin, but it's very similar also, for example, in healthcare or in buildings. So they are not really connected, they are not really secure yet. So that's what the future will bring, hopefully. But this is a huge challenge if you want to build digital twins of this data, right? So the trend is that there is an evolution of this IT and OT convergence. So OT is the operational technology, so more the machines and the factories, and the IT is the software which we build with that. So this is connecting to each other more and more. For each new shop floor you now build, it's more connected, obviously, and uses more standards, but most of the things today are still all this old stuff. So you have to connect it somehow. And this is a huge challenge, even if the trend is to connect it more and more in the future. So to building digital twins for all the use cases we have seen, this is really complex today. Complex regarding things like scalability and real-time processing, but also regarding cost, because often you need to use proprietary protocols and buy very expensive software with expensive licensing. And that's often the main blockers to build digital twins. And with that, of course, there's a huge demand to build an open and flexible and scalable platform. And that's in the end what this talk now is about, how you can leverage open platforms to build such a digital twin infrastructure. often together with some IoT platforms which are proprietary for connecting to specific machines. So that's totally fine to combine these, but here is some of the requirements which we see more and more to build a highly scalable and less costly and flexible infrastructure. And that's what I will cover now in much more detail. So let's first talk about IoT platforms in general. And in general, I mean, there is 600 or more on the market available, right? This is very different things. Some are for very specific problems and some are more generic, or some are just available in the cloud. So it's really important to understand that there's a lot of products available in the market, and you probably never will find out what all of them do. And with that, let's take a look at a few of them. First of all, one of these things is proprietary IoT platforms. And here's really just a few of the examples, like Siemens MindSphere is very common in Germany, for example, or GE Predix is used a lot in the US, and there's others like Cisco Kinetic and many, many more. What's great about these platforms is they are really sophisticated in integrating with the IoT edge interfaces, often with proprietary protocols. So if you have a lot of Siemens machines, for example, with S3, S5, S7 proprietary protocols, then of course Siemens MindSphere is great to integrate with them. That's what it's built for. On the other side, however, what's not really working that well is that it's not really built to integrate with the rest of the enterprise at scale in real time. So typically it's good for some parts, but not for others. And also licensing, and it is really hard because of course it's often pretty expensive and it's not really extendable because it's not open. It's a commercial platform, which is totally valid, but not good for everything. And then of course there's these IoT offerings from cloud providers. So every big cloud provider has one, like Azure, AWS, GCP or Alibaba. They all have IoT cloud offerings. And actually, while of course they mostly focus on the cloud and their services there are like an integration layer for IoT from the devices, or device management or shadowing, they also more and more provide software for the edge, because they want you to deploy their software at the edge to integrate with their cloud and ingest everything to the cloud. So here's just one example with the Azure IoT platform, where you see that they have a cloud gateway and then other analytics capabilities in the cloud, which are often their common services, which you can then simply combine also with the IoT specific products. But also here at the top you see, for example, Azure Sphere, which is in the end a technology so that you can even embed Azure interfaces into the devices at the edge. And this makes some things easier, like secure communication. But of course also it has trade-offs like vendor login. You have to use this cloud provider then often. And there is always some trade-offs with using this. But the main blocker, I think, is also it's proprietary, and so it can get very costly, and then it's hard to switch also to another cloud provider, for example. And also because in IoT and digital twin, we typically have projects where not everything can run in the cloud, but many things have to run at the edge, in the hospital, in the factory. And therefore, a cloud can be a part of this story, but typically it should not be just a cloud solution. And therefore, on the other side, of course, there's also standards-based solutions and open source frameworks which you can use. So some open source frameworks are from IoT Eclipse platform or PLC4X, an Apache framework specifically built for connecting to proprietary industrial IoT protocols like Modbus or Siemens S7. And then, of course, there is others like MQTT standard, and then vendors behind it like HiveMQ. So the trade-offs here are often either you have to pick one specific solution for one specific problem. Like if you want to integrate with MQTT standards, then something like HiveMQ is a great solution. It's open core, so this means open source, but you have a sophisticated platform with scalability and security if you want to buy the commercial solution. That's great if you want to integrate with MQTT. But if you have then an overall problem, like you integrate with many different things, then you would choose something like Node-RED, which provides this connectivity to many things, but therefore, in contrary to HiveMQ in this example, it's not really built for mission-critical scale with the vendors behind it. So there's always trade-offs if you choose open source and standards. Either pick it for one specific things where it might be great, But if you want to have it more generic, then you need to really be sure that you get a vendor behind this. So with this then, we understood that there is many different IoT platforms with different characteristics, all with their benefits and with their cons. So now let's understand how Apache Kafka as event streaming platform fits into this, to later discuss the architectures. In this talk, I don't want to cover Kafka in detail. I've done it so often and there is so much other material on the web. So if you don't know Kafka well, please also check out other material. Here I really summarize it that Kafka is built for scale and it's built for real time. And this combination makes it very powerful. And also it's not just a messaging system. So it's a combination of messaging and storage. So it decouples all the different producers from the consumers, and you can store data in Kafka as long as you want. It's not like a queuing system. And also it provides capabilities for integration and for processing data. So it's much, much more than just a messaging system. That's why it's called an event streaming platform. And it was built for scale. Again, I will not cover details here, but here you see just a few of the examples where it's really built for large scale. However, having said that, it's not being used only for big data projects, but also more and more for transactional data with smaller data sets. And obviously also not just used by the tech giants, but more or less by every company on this planet, right, which is using it for a lot of IoT projects. So here's just a few examples. I will not go into detail here. Check out the resources later. Just remember it's used by many different industries and companies. So there's so many use cases for Kafka. And IoT is just one specific scenario for Kafka. Kafka in core is a distributed commit log. So this means producers produce data and different consumers are completely decoupled and consume the data like they want, either in real time, in near real time, in batch, or maybe with request response with HTTP. And the log always also stores the data event-based in guaranteed order. And it's immutable. You cannot change these events. So this is perfect for many use cases like event sourcing or for reprocessing events. And with that, of course, it's also a perfect fit for IoT and digital twin. Another important part is that Kafka allows you to create data awareness. This means that you can configure and define schemas for the different client applications, which could be the machines and the sensors, or it could be the CRM application or the analytics tool or the digital twin database. No matter if you use different technologies for all of that, you have one central concept to define the data in the schemas and even with the evolution of the schemas. And that's really huge when you want to integrate all of this to build a digital twin infrastructure. However, having said that, it's important that with Kafka you can really build your own domains and decouple the different things. So here you see an example where Kafka is the central event streaming platform, but you integrate with many different components. So in this example, like in the bottom left, an IoT domain which uses Kafka Connect and MQTT for direct integration with some devices. On the other side, in the middle, you see a legacy domain where you use, for example, an existing IoT platform to connect to OPC UA interfaces, which could also be in a factory with standards, right? And on the right side, you see an analytics domain. Here you use cutting-edge technologies to build and train new analytic models. This might be a Java application or maybe something like Python and Jupyter notebooks where you train your favorite machine learning models with TensorFlow or H2O or a cloud service. And this is the great thing about Kafka. It decouples all these different components and therefore it's really huge, especially in IoT projects where you have so many different technologies and platforms and somehow want to integrate them, but still keeping them independent from each other for development, for testing, for scaling, for replacing. And that's why Kafka is so great here. Again, I don't want to go into much more detail into Kafka. Here's just quickly showing you 10 reasons why people use Kafka for event streaming and also for IoT projects. Like it's highly available, mission critical, real time, it's open source. So it's really huge. And as I said, it also combines and integrates features for connectivity and for processing the data in real time at scale. And you can use it everywhere, at the edge, in the data center, in the cloud, multi-cloud, or a combination of all of that. And that makes it so comfortable to use Kafka in IoT projects. And once again, I want to talk about how this is now related to machine learning, because as we heard in the beginning, digital twin and machine learning, it's very complementary and typically used together. And obviously, Apache Kafka is a good fit here, right? So if you want to do continuous learning and monitoring and acting, then you, in best case, you do that in real time and at scale. And that's exactly what Kafka is built for. And for machine learning, you need data. The more data, the better. And you need to pre-process the data to have good data quality and the right data to train your models. And also then the same for model deployment and monitoring, for scoring. And here integration and data processing are key, at scale in real time. And this is what Kafka brings, right? So it's a perfect combination. So I don't also want to go into more detail here. There's so much other material also from me, which you can check out, like blogs, videos, and slides about how Kafka and machine learning are related. So the big problem now here is, and that's what you might think now, hold on, Kafka is not an IoT platform, right? And that's completely true. So we need to think about where Kafka fits into this story and how you might want to combine it with other platforms or technologies. So some things Kafka is not very good in. So let's also be very honest here. So Kafka is not the best thing for everything. So from IoT perspective, Kafka, for example, does not provide you anything for device management or shadowing, like the cloud services do, for example. It's also not built for unreliable networks. So this is where MQTT, for example, is great. It can connect from the driving cars, even if they drive through the tunnel without internet connectivity or with network spikes and all these things. And that's not really what Kafka is built for. And so also if you want to connect beyond standards, so really these kind of proprietary legacy technologies. That's what Kafka is used for a lot in banking, like for mainframe integration. But the same is not true for IoT, where you want to connect to these PLCs, where you connect really directly to the machines. However, this is very complex and proprietary. So you might use an IoT platform like Siemens MindSphere for that. And also for edge hardware. So sometimes we see more and more deployments of Kafka at the edge, but this really needs to define what the edge is, because Kafka cannot be deployed on a microcontroller, right? At least not the server side of Kafka. You could deploy a C or C++ client on a microcontroller. But therefore you see, Kafka is not the best fit for everything, and therefore let's understand how it complements other IoT platforms, and then also how to build a digital twin infrastructure with that. That's in the end what I now want to cover. So let's talk about the spoiled for choice for building a digital twin. Before we talk about different platforms and technologies, let's understand in more detail the characteristics of a digital twin. First of all, the key thing is connectivity. You want to connect to all these assets, which can be physical devices, which can be a process, which can be a human. So connectivity and bidirectional communication is really key for success. And obviously, in most cases, in real time, at scale. The other important thing about this is homogenization, which means that you want to build a standard kind of integration, but still decouple all the different components, because the sensors still produce data, and the real-time analytics tool might need some back pressure, or you might want to start a new application to consume the data. So it's important to decouple everything, but have data awareness and standards, for example with schemas to define the data structure, and then to allow multiple agents to consume the data, no matter where these agents are. So if you think about a hospital, some processing might be locally, but some other processing might happen in the cloud, where you do some more analytics with the anonymized data also. Right? So this is really also key. And then being reprogrammable and smart. This is just another term from IoT perspective, thinking about microservices and being agile and developing new applications and new business logic, deployed easily, deploy different versions of business logic, try out which one works better, do things like A/B testing, canary testing, all these kind of things. It needs to be flexible to be successful with digital twin technology. Also, for example, to build a new version of a product by analyzing the digital twin of the old version and then improve the next version. Digital traces is also key. Obviously, with a digital twin, we don't just want to ingest data, but we want to store the data in a trace so that we can analyze it. For example, to diagnose problems. And what's happening under the hood? You want to consume all the events which happen from the different sensors of a machine or from the human information which you got. And then you want to analyze and correlate the data. So it's important that you install each event and not just the aggregation of it, so that you can use it in the way you want to do that. And then modularity is of course key, so that you can define this architecture like you need it. Like you can combine an IoT platform for integration with the devices together with the real-time correlation and streaming analytics with Kafka, for example. So these are the characteristics of how to build a digital twin. And now let's take a look at a few different examples of architectures. This here is now the general pipeline. No matter which technology you use, the main idea is you have some kind of assets, like on the left side with different integration standards or proprietary protocols, and you want to get that data into some platform to use it, to correlate it, to process it. And one of these outputs is the digital twin for the use cases we discussed in the beginning. In addition to the digital twin, you typically also have other use cases, like for example, for doing some kind of analytics or BI dashboarding, or for combining it into completely other business use cases, or for providing access from your mobile app with request response, right? So this is now the simplified pipeline for a digital twin. And now on the top right, you always see these 5 characteristics for digital twin: connectivity, homogenization, reprogrammable and smart, digital traces, and modularity. And I now show you 5 different scenarios and architectures, and we'll always discuss these characteristics there. The first scenario is you build a digital twin with a monolith. So you just use one single IoT platform and build your digital twin with that. This might work great, right? You can connect to the devices from there and build your digital twin. However, well, it's not really decoupled from everything. So if you also want to build other applications, where do you connect them? And which technologies do they have to use? So you're not really flexible. And also when you want to build then new applications with another technology, it's really hard. Also regarding digital traces, it depends what this IoT platform uses under the hood. If it's just a database or data lake, well, if they have a data lake, then you store everything at rest, often even already in consolidated form. And then it's really hard to reprocess all these events in guaranteed order again and again to do diagnosis and so on. So, and also the modularity is not really given because it's one monolith, one platform. So for some use cases it works, but it also has a lot of drawbacks. So therefore, let's think about scenario 2, building a digital twin as external database. So this means that you use the IoT platform for connectivity, that's perfect, but then you also connect to another database. This already decouples things a little bit, so then you can build your digital twin and the dashboards and the analytics in its own separate deployment and infrastructure, which you might even then move, for example, from one factory to the cloud so that you can build a digital twin for several different factories. So this makes it much more easy, but still you have the trouble with building other applications around that, because then you first ingest everything into a database and then you have to consume it from the database, from the data at rest again, to build new applications and logic against it. That's not really perfect for many scenarios. And also, depending on how you define the digital trace, you might lose information. It might not be event-based anymore, but more like a data lake kind of version of the data, right? And it's still not really that modular because, yes, you have your IoT platform and your digital twin, they are separated, but this is still 2 big components and more like now 2 big monoliths which you have. But still again, I'm not saying it's bad. For some use cases, it's the right choice. So scenario 3 is then when you introduce Kafka as backbone. For all the reasons we discussed before, you have Kafka in the middle as central event streaming layer. It provides the connectivity on the one side to the IoT platform, which is doing all this complex integration with the legacy products and with the proprietary protocols of the machines. And on the other side, you also integrate to the digital twin database. So with this now, we have all the connectivity given. However, we have a much more decoupled and generalized architecture. You can now easily also connect and consume the data from other applications, like you see in the yellow examples here. And this can be real-time, this can be batch, this can be mobile apps with request response. They all can consume directly from the event-based log and take the data like they want it. So with this, you can easily build new applications completely decoupled. And also, out of the box, Kafka provides this digital trace because it's a commit log under the hood with immutable events. And you can store it in Kafka as long as you want to consume it from other applications. Still, you have the advantage of the digital twin capabilities in your database. Like this could be something like a MongoDB for document store, or something like InfluxDB for more like time series analytics. That's totally fine and separated and great for this use case, but it's just more a modular architecture where everything can be used exactly for what it is. So you're going away from the monoliths and decouple everything and can scale everything by itself. And with Kafka in the middle, you have an open, reliable, and scalable infrastructure as the core-based system. And that's really a huge advantage here. Scenario 4 is actually similar, but here you don't use another IoT platform. So this means you directly connect from Apache Kafka to the assets, like the machines or the sensors. On the other side, it's the same story. So we have all the connectivity. However, the connectivity to the edge is more like Kafka Connect, for example, and MQTT connectors. Or, for example, use a framework like PLC4X to directly connect to machines with proprietary protocols like Modbus. So a lot of connectivity in both directions. However, a little bit simplified architecture because you don't need the IoT platform anymore. Of course, with all its drawbacks, right? So for some things, an IoT platform is better than Kafka. The other advantage is still you have all this generalization and decoupling with schema management and so on. You can easily build new applications around that. The digital trace is in Kafka, so that's great. And you have all this modularity because you can scale every single component like you want. And even here, for people who don't know Kafka that well, even in Kafka you have this modularization. So Kafka is not one monolith, it's a distributed scalable system. For example, with 3 Kafka brokers, 2 Kafka Connect instances, 2 schema registries, and some processing units. So all of that is separated from each other to be scalable and independent. And so this is really much better modularity. So this is also a great solution. And the 5th scenario is where you actually use Kafka as digital twin. So this means, like you see on the right side, there is no other database used for building the digital twin. You used Kafka as digital twin. You use the distributed commit log for storing all the events in a digital trace, which you do anyway. And then you can directly use this for further processing, for doing predictions, for doing anomaly detection, for doing aggregations of the data. Also for doing some kind of BI on top of the Kafka data, for doing SQL queries and pull queries on top of that. So this is absolutely possible. So you can store data in Kafka as long as you want, especially now with features like tiered storage, where you don't keep everything in the Kafka brokers, but also in a remote object store like AWS S3, for example. So you can easily store data in Kafka long-term or forever. The huge advantage is it's still guaranteed order and event-based, and you can reprocess and consume the data again and again, and still it's scalable in real time. That's the huge advantage of this architecture. Of course, the drawback is you have to think about how do you want to query the data. With Kafka, you have some limitations here, and either this is good enough for you, or you can also use a SQL layer on top of Kafka. So, for example, with a tool like Rockset, which is a Silicon Valley startup, they provide a ANSI SQL layer on top of Kafka. You can even connect Kafka to your favorite BI tools like Tableau or Qlik or Power BI. So this is all doable, but it has some trade-offs. So you don't have all the advantages like before of the separate database like a MongoDB or Influx or Elastic with the advantages it has, right, for the specific use case. However, from this perspective, then we come back to the discussion, do you have just one digital twin or more of them? In many cases I see, for one example, you want to be doing real-time time series analytics. And therefore, in addition to building this, another consumer could be the time series database, which is another kind of digital twin. Again, think about these 5 characteristics at the top right and how you want to implement this for a digital twin. There is no best solution. It simply depends on what you want to do. So this was now 5 different scenarios, all with their trade-offs. Finally, just again, I discussed this already. Kafka is a database, seriously. So yes, seriously, but of course not for every use case, right? But again, remember that Kafka is a distributed commit log. You can store data here forever, event-based guaranteed order in an immutable log. And then everybody is decoupled and can consume the data. So that's the first part. And then, as I already mentioned, with tiered storage, which is now available already as a product from Confluent, only in Confluent platform, but also there is an open Kafka improvement proposal for the open source framework to discuss how to implement this as an open source API and interface for Kafka. And with this, you really can implement long-term storage in Kafka easily. So you shouldn't worry about this too much, especially then with tiered storage capabilities. And also, what's important in Kafka is that it's not just the server side where you store data, it can also be the client side. Because in Kafka, you can not just build stateless clients, for example, for streaming ETL, but you can build stateful applications. We have use cases in other industries, like in banking, where you build instant payment apps or some cross-selling for your customer experience. But the same is true in the IoT, where you can keep data in the client. And therefore, you could also build a digital twin in the client where you keep the state. So each instance or each information about each digital twin is stored in a Kafka client, all backed up by the Kafka server side, right? So you more or less build materialized views in the client app. This can either be just in memory, but in most cases it's also stored there for high availability. And this is actually in Kafka and event streaming a common thing to build stateful clients. And if you reconsider now what I discussed about a digital twin is, so for some use cases, it might just be a Kafka client where you keep the state. And this is just for you to keep in mind that a database can be many different things. And for some use cases, it can even be just Kafka. So, and with that, then you can also build stateful client application with technologies like Kafka Streams or KSQLDB, for example. So I don't want to cover this in more detail here, but I also have written an extensive blog post about discussing if Kafka can replace a database. So this is a very controversial discussion. And to have a short summary here, the answer is yes, it can be a database, but it will definitely not replace all the other databases like an Oracle, an MongoDB, an Influx, whatever you use, right? So for some use cases, Kafka is great as database. And always consider, do you mean the server or the client side of Kafka for talking about data storage? And also, typically, Kafka then is combined and complementary to other databases, like it is complementary to other IoT platforms. And that's the great thing about it. But if you have Kafka as the central layer in the middle, you have the high availability for real-time and scalable data sets. And with that, you can then complement this with other databases for specific use cases, like real-time analytics with a time series database, or like a data lake with Hadoop or S3. And then you also use MongoDB for document analytics or storage. That's totally all fine and valid. So with this, let's also talk a little bit about global IoT architecture. So how could you now use what you have just learned for building a digital twin? Because this is really important. So when we see digital twin discussions at our customers, it's often a hybrid discussion. So you think about the edge, where the factory is, or where the hospital is. But then you also have more a centralized location where you want to aggregate the data from different sources. And then, of course, cloud is a big topic there. Right? And in some cases, it's even a global architecture because you want to correlate the information from different continents. So first of all, let's talk about the edge. So at the edge, we see more and more Kafka deployments. Obviously, it's important to understand or discuss what the edge is. The edge could be a factory where you can easily deploy a big cluster of Kafka if you have more or less like a data center in the edge. Or it could be just a retail store, or it could be each doctor in each village. So there, typically you have just a small kind of piece of hardware which you want to put there and connect it to the Wi-Fi, and then everything else has to be pre-configured and run in there. because there is no data center and admin people there. And therefore at the edge we see more and more Kafka deployments, often also just one single broker. If you can live with no high availability, for some use cases it's good enough. In healthcare it's often not, but in some IoT scenarios, in industrial IoT it is. Or in retail stores, for example. And then with that you can either have your digital twin at the location at the edge, if you want to do local processing and state storing there, or you replicate the data to another central cluster, right? So this is in the end what I mean with edge digital twin architecture. And then based on that, you can build a centralized digital twin. In this example, we used Confluent Cloud. So this means we have a cloud infrastructure where the Kafka part is fully managed with SLAs, with consumption-based pricing, so that you just use it as a service. And you connect from that to all your edge deployments, where you replicate the data from to the central cluster. And then you build your digital twin here with the central Kafka cluster. And this is then the same discussion. So the digital twin could be an IoT service from Azure. It could be part of the Kafka infrastructure. It could be MongoDB Atlas if you want to use another cloud service. And as you see here, even at the edge, it's not all the same typically. So we see more and more people using Kafka at the edge, because then they can use the same architecture and technology and APIs at the edge and in the central infrastructure. However, like here, two of these kind of factories might use something like Kafka and in the same template way. However, one other has already Siemens MindSphere and connects to the Siemens machines, maybe in Germany. That's totally fine and valid. And then you can all aggregate this data and maybe transform and enrich it so that it has the same structure and information, and build your digital twin with that. And then with that step, of course, in some scenarios you might even go global. So here we see an example of a global digital twin architecture, whatever that means in your use case, right? This is really just to show you the flexibility with Kafka and with Confluent, what we see at our customers, that people deploy different kind of infrastructures, but still somehow they want to integrate these architectures with each other. And the same is true for digital twin, like it's true for everything else. Kafka is a perfect fit here because it's doing reliable and scalable streaming of data in real time, but still it can guarantee that you don't lose data if some of the infrastructures are down. And of course, if you're hybrid or global, the likelihood that something is down is higher, right? So with this, then we have different architectures and design options how to build regional or global infrastructures. And the same is then true for digital twin. This doesn't really change from general Kafka recommendations to digital twins and IoT architectures. Here's just one example where we even can build a multi-region digital twin, where we really can guarantee zero data loss and zero downtime for this digital twin. And this is really huge. So you have automated disaster recovery, but still zero data loss, even if a data center or region is down. And this is just now part of this architecture which you can build with Kafka to support a digital twin, even for 24/7 use cases without data loss. Here, similar to the other discussions about machine learning and so on, I could talk for a long time about this. Here is more material where I have a discussion just about architecture patterns for Kafka, for hybrid, edge, and global. And everything you see here is also applicable to digital twin and IoT architectures. So with that, let's just think about one example to conclude this. A digital twin for a connected car infrastructure at scale in real time. Here now is the example. So we have ingesting data from 100,000 cars in this example which we built, and ingest this with MQTT to the Kafka cluster. And then on the top we do some processing of the data, and then we also do some model training. And then finally we also deploy these models into another Kafka application for real-time scoring. And at the bottom right, we also see that we ingest the data into another database, like in this case, Elasticsearch, right? And now, if you think back with this architecture in mind and this use case about the characteristics of a digital twin and how to implement this, what do we have here? We have the connectivity between all these different systems, and you can choose per use case where to store your data. So in your definition of a digital twin, it might be the Elastic cluster where you can do search and queries and aggregate the data even more. So this is given end to end from the edge and the devices, in the cars in this case, to Elastic, but also to other applications which consume the data. Homogenization is there, you have data awareness, you can integrate many different technologies and standards, like in this case, we have JSON data coming via MQTT into Kafka, and then we use a better format with Afro or Protobuf to compress the data and give it a structure with schemas, and then with the schema in place, everybody else can consume the data. And it doesn't matter if then it's stored just in Elasticsearch, or maybe if you have another consumer of the data which stores it in Hadoop, in Parquet or so. That's all decoupled from each other and still standardized, and you're totally flexible with that. And with that, it's also reprogrammable, so you can easily add new applications or services, even in completely new technologies or with new databases in mind. And in the same way, of course, you can also now add other technologies, like in addition to the real-time data from cars, which stream data, you might use another IoT platform at the edge to also connect to the factories. And then you can correlate the data from the factories with the real-world data of the cars to get new added value out of that. As in this case, Kafka is the digital tracing, you also have all this information in guaranteed order in the log of Kafka, immutable, and as long as you want to store it here. And the modularity is also given, so you can scale every one of these components up by themselves. It's highly available by themselves, and then you can also add new modules here. And that's really huge, right? So you're very flexible, but still scalable and can do real-time processing where you need to do that. And therefore, while actually, to be honest, when we built this demo, we didn't have the digital twin term in mind, but actually that is what it is when you think about the definition of and use cases of a digital twin. And so I also will not show the demo here. We have another YouTube video where you can take a look, and also feel free to take a look at the GitHub project to get an understanding of how this was built. Intentionally, we built this not with cloud services, but really on Kubernetes. So that this is more like a template architecture where you can choose your own modules and add what you want. So right now, while recording this video, I'm in the process of adding MongoDB and InfluxDB to this demo here, so that in addition to having Kafka consumers for real-time model scoring and training with TensorFlow, we also build more or less like a digital twin with Mongo for document search and with InfluxDB for real-time time series analytics. So decide by yourself what parts of this is a digital twin or not. It's just a definition and term, right, and a concept. But I think you can see the huge added value of this scalable and flexible architecture. And with that, let's conclude again. So a digital twin merges the physical and the digital world. While it's not just physical assets, it could also be just a process or a digital service which you want to get a copy of to do simulations and so on. But I think we all agree you can get a lot of added business value in many different industries. And manufacturing is the most important one, and Industry 4.0 and automation industry. But it's also for healthcare, for buildings, for smart city and many other scenarios. And therefore, I hope you got an understanding how Kafka fits in here with event streaming. It's open, it's scalable, it's reliable. And therefore, it's really a perfect complementary solution combined with other IoT platforms or frameworks or standards and with other backend applications and databases. And with all this knowledge, I hope you can also now build your digital twin. And I'm also happy to get your feedback on this session. Please let me know, and please sync with me on LinkedIn, on Twitter, and let's connect to have more discussions in the future. Thanks a lot for watching, and let's now build our own digital twins. Thank you.